well, for those of you who don't know, my name's Carl Toland. I'll be presenting the advancements in the development of the WeG, which is the MEMS gravimeter that we've been developing for the Newton G project. Apologies for myself not making it to this meeting. I would have loved to have came, but we're kind of at the tail end of all the teaching commitments at the moment, and we've all been quite busy and unable to travel for it. But remotely, we've got myself and Abhinav, and in the room we should have Henny and Phoebe. I'll let them put their hands up if you don't know them already. But yeah, we'll move on to talk about what we have managed to achieve throughout the Newton G project. So just a quick overview. So we can give you an introduction to WeG, but before the Newton G project started. The aim of that is to really emphasize where we've came in this whole during the whole period of the project, and how we've managed to make it into a field portable system. We'll then briefly talk about the deliveries of WeG to INGV. As Daniel said already, we have 4 systems on there, so we'll give you the little story behind that. Evolution of WeG during Newton G, so all the things that we've learned throughout this project and how we want to implement changes to next generation systems. And then touch on what systems we currently have on Mount Etna and the future opportunities for collaboration beyond Newton G. So, well, we're all aware of what WeG is now through various different presentations. It's always helpful to, at the end of the project, when looking back over it all, to see where we started and what we had and tell the story of how we got to where we are today. So prior to Newton G, we had a shadow sensor set up, which was led by Giles, Richard, Doug Paul, and others within the group at Glasgow. And they managed to measure earth tides for the first time with a MEMS gravimeter. And that was published in Nature back in 2016. But as you can see from the photograph, there were racks and racks of equipment and large vacuum tanks that were needed to obtain these results. So after that, the goal was, well, how can we miniaturize the setup, but also get it into a form where we can make it portable? So that was in 2017. The team at Glasgow were able to miniaturize their optical sensor MEMS gravimeter from a big vacuum tank into the little metal cube that you can see pictured on the right-hand side. So that little cube, we could evacuate it, and you can see from the photo of Richard sitting next to it. The electronics is no longer on racks of equipment. It's now kind of miniaturized into these bespoke little electronic boards. But as you can see, even though this was a portable system and they were able to take measurements outside, which they published there, put a little DOI there if you want to go look at it in the future. But you can see it was still in the prototype stage. All the electronics were still bare. Everything was kind of, not as robust as you would imagine it to be in terms of connections. So it showed, though, that the potential for the future development to turn it into a robust instrument was there and possible. So that led on to our little change in design. So we no longer went with the optical shadow sensor setup, but we started looking into the capacitor sensing setup. So currently, current WeGs, we use this capacitive sensor to take all the measurements. And this was proved to be successful back in 2019. With the capacitor sensor setup, they were able to measure earth tides again, this time over a 19-day period. But again, this was in the early days of the capacitor sensor. So we were still back to using the racks of equipment and a big vacuum tank in the lab. So really, now we have to get this form factor into a portable one, and that's where the Newton G project came in. So Newton G provided us a opportunity to take all the development that we've had for the optical shadow sensor and then the capacitive sensor to evolve it into a MEMS gravimeter, which is no longer a lab-based system, but to a fully portable, IP-rated, user-friendly system, which we all know now as Ouija. And we knew that there would be several challenges. There's a reason that we had to put it in big vacuum tanks to start with to kind of characterize the system. So we know that we would need a thermally stable enclosure. So because silicon is very sensitive to temperature changes, we had to ensure that we could control the MEMS sensor to sub-millikelvin level. We know it had to be IP67 rated, because not only for Newton G, but here at Glasgow, it rains quite a lot. So if we want to take it outside, we have to make sure that we have a IP-rated system that we can use it in. We also have to combat sensor drift. So that sensor drift is something that I think every gravimeter will have to combat. So that was one that we had to do as well. For Newton G specifically, we wanted the ability to adjust the tilt of the sensor remotely. And we also had to establish bespoke data comms set up to allow us to pull the data from the Ouijas, both locally and remotely. And most importantly, we need them to survive being transported from Glasgow all the way to its end destination on Mount Etna. So during the development of Ouija, we went through a lot of prototypes in terms of all the different parts internally within the Ouija. So, for example, the thermal enclosure, which Christian Anastasio, which most of you might know, he had a big role to play in design of the thermal enclosures for Ouija. There was a lot of wire debugging in the initial development phase of Ouija. Excuse me. And we also had a lot of changes to the MEMS sensor layer to incorporate new features or design changes. We also then had more debugging, and you can potentially see a theme throughout the slide. We had optimal positions of temperature sensors to deal with as well. Basically locating all the sensors in the optimal place such that we can control the MEMS device with as little drift as we can. Following that, there was more debugging, and we then went through several design iterations of the electronics boards, which then also led to more debugging. So it was always debug, every other stage it seemed. So it was a very tough challenge, but we did get there in the end, which is nice. So overall, before we had the main Ouija sensors that we all know now, we went through two main prototype systems. So we had RP0. So RP stands for rapid prototype. And we had RP 1.1. So the reason they're called rapid prototypes is because at the time we were currently finalizing the last design stages for the final Ouija system. So we were experimenting with different ways that we can basically install all the internal components while waiting for this to be made. So RP0, which you can see on the left-hand side, so that was actually made in-house by us during first COVID lockdown. So we basically had to work with what we had because we couldn't really do anything at that point. And because RP 1.1 at that stage was currently getting manufactured. However, both systems, even though they're rapid prototypes, even though the RP0 looks very unique, if that's a word for it, they were both able to be used both locally, indoor and outdoor for field trials. So for example, we've got a photograph here of RP0 and RP 1.1, both on a bridge that we use regularly to characterize systems in Kelvin Grove Park in Glasgow. So eventually we managed to get a final design and multiple Ouija enclosures all made up for Newton G. So photo from here, so white enclosures we basically got them delivered in batches to us, because the goal was that we could potentially put them together in batches as well. But that actually provided to be quite a bit of a challenge, just assembling one of the systems. So it was a massive group effort from everyone at Glasgow. Everyone from postdocs to the academics to the PhD students, we all had our own roles. Even the summer students and undergrads all had specific roles to try and figure out problems and challenges with assembling these systems together. So for example, assembly, myself, Christian and Nabnav did a lot of that effort. We had Henny and Phoebe at the workshop today, helping a lot with field trials. And Phoebe also, which I'll mention later, also helped with delivering one of the systems to INGV. In fact, no, several systems, sorry, to INGV. So it was a massive team effort. Everyone played their part, and it was a very nice achievement to get them out of Glasgow and over to Catania. So we'll move on to the deliveries of these systems. So we had multiple sensors delivered. So as Daniele said, we've currently got 4 on Mount Etna. And due to COVID restrictions, initially that kind of limited what we could do at the time. So we actually sent one of the rapid prototypes, RP 1.1, as our first delivery. So that was sent out by Christian and Stephen Bramseep. And this was followed by a second delivery by Christian again, and also Phoebe. But that was the first of the IP67 rated Ouija systems. So both of these systems were fully assembled in Glasgow and then sent over via hand carry with them on a plane, which although proved a bit awkward, imagine, that we were still able to get them there. But this limited us to basically one system at a time. So a third delivery, which was made by a combination of Abhinav and Phoebe. This was the first where we went for a multi-sensor delivery, where we basically sent over all the enclosures without a MEMS sensor, and Abhinav went over on a short-term attachment where he got some funding for. And while he was at INGV, he was able to finalize putting the systems together with just standard capacitor setups, while Phoebe then brought over on the plane a total of 4 MEMS sensors, which combined, they both installed into Ouija systems within INGV. Unfortunately, one of the sensors had to come back to Glasgow, so that's why there's not 5, there's only 4. But this turned out to be a safer and more convenient way of delivering multiple sensors. So it's definitely one of the main benefits that we learned throughout the process of, throughout the project of Newton G when we wanted to deliver these systems. So the deployment of Ouija on Etna gave us a new environment to work in. There wasn't a lab, that wasn't Glasgow, where we managed to learn some new things. So, for example, robustness of being able to bring something from Glasgow to Catania was one of the major issues we wanted to fix. So we went from using individual wire strands for all our connections to using a bespoke custom-made flex cable. That made it more robust. It made it easier for debugging, so less prone to shorts unknowingly happening. As Daniele touched on in this presentation before me, long-term measurements on Mount Etna provided a potential ambient pressure change sensitivity, which we weren't able to find at Glasgow. Basically, all our pressure changes are short-term when we look at assembling the systems, whereas these were the more long-term ones, which our system became sensitive to. So we have now looked into the sealing process for our MEMS packages, which currently we do manually within an argon atmosphere. And we're currently investigating more robust ways to carry out this for next generation sensors. So that's making some progress internally. We know the challenging thermal environment, basically the large changes in temperature we can get throughout the day, depending on the time of year, has showed long-term sensor drift on our sensor. And again, research is currently underway, making design changes to several of the main components within the WEG to implement in the next generation to reduce the temperature-induced, to reduce the temperature drift that we're seeing on our sensor. The location of the step motors that we would use for remote control turned out not to be optimal in terms of the internal space and heat dissipation. So we've since removed all the internal step motors within our sensor, and if we do plan to use them, they would all be external now. So we would make an external stand to put the WEG on, to put those step motors on. And also use of the WEG by non-Glasgow members have highlighted areas of the GUI, so the graphical user interface, that you would use to control the WEG, to make it more user-friendly. This will be an ongoing thing. This will always be getting updated, but we've taken all the feedback on board and implemented those changes onto the sensor. So just quickly, just realize the time. So basically, we currently have 4 systems on Etna. They're kind of ECPN, EPDN, EBEL, and SLN. And here's just a snapshot of one of the sensors. So this is on SLN of RP1. And you can see it's fitting very nicely with the earth tide. So this was taken between December of last year and February of this year. So it's very nice to see that our sensors are working outside of Glasgow, which makes us all feel good. Future opportunities. Discussions have already been taking place for future collaborations beyond Newton G with our next generation sensors. So I've already spoken with Danielle and a few others about possible opportunities there. We're always open to opportunities to trial next generation sensors that are currently being manufactured and integrating changes that we've learned from Newton G in collaboration with INGV on Mount Etna. And we'll also continue to apply for funding to allow us to conduct field trials similar to our short-term attachment they did this year. So just to conclude, Newton G project, we feel, has been a very positive in terms of impact on the field as well as the development on the WEG system. Despite challenges throughout the project, such as COVID, we were still able to deliver systems, which I think is a major positive in terms of the project. Currently, the greatest concentration of WEG systems is on Mount Etna. So believe it or not, there's more WEGs there than there is in Glasgow. And also the challenging operating environment of WEG has allowed us to make several of the upgrades to allow them to be more robust for the future. And like I say, there are hopes to do further collaboration with more WEGs down the line. But most importantly, the Newton G project has brought many great minds, many great people, many great institutions together. We thank you all for the work that you've all put in, all the great discussions we've had, all the different presentations, all the visits, and we look forward to working again in the future. And there's a little photograph of the group. So just in case you don't know, Richard on the right here has left us now. So he has moved on to move up north and over to the Isle of Lewis to basically take a whole new career change. So just in case you didn't know, he's left the group, but he's still in contact, and I think he sent his details to those who want to keep in contact. So thank you. And I'll pass on to